Thank you. Mic test. Okay, this works. Yeah, first of all, thanks to Eric and Tom for organizing this workshop. This is a quite special occasion to me because, in fact, knowing Martin has been extremely beneficial for me in the early days of my life in UK academia. And I would like to say some words on when I first, or how I first met Martin. So I started doing type theory around, I think, 2009 probably. And so in 2011, I started a PhD with Thorsten in Nottingham on homotopy type theory. Just that Thorsten didn't like the word homotopy, so we called it higher dimensional type theory. And I just sneakily changed this title one day before the submission of my thesis. Right, so I mean, nowadays, like lots of people do homotopy type theory, and there are like 1,000 papers which have a title like X in homotopy type theory. That was not the case when I started. So one difficulty for me was that there was not that much work internally in homotopy type theory. So I mean, at that time, I think Peter Lumstein's thesis had just come out on higher categories from type theories, and then there was work by Gambino Garner and I think Gambino Vandenberg and Audi Warren and probably lots of other work that I forgot. But like most of this work was meta-theoretically. So there were not as many examples of work that you actually can implement in ACTA, because at that time also I already had been hooked on ACTA. And there were just not as many examples what one could do with this new framework of homotopy type theory as they are now today. Right. So essentially, Thorsten told me about go and find out what this higher dimensional homotopy type theory is, and then come back and explain it to me. So I tried doing that. Yeah, so most things that I learned at that time, I actually probably learned from Mike Schurman's blog posts. But I didn't really know what I was doing, so I just looked at papers and waited to have an idea about these topics. And so at some point, I learned about Michael Hedberg's theorem, who wrote this paper on a coherence theorem for Martin-Löf type theory in 1998, and he formalized it in ALF. And his result essentially states that if a type has decidable equality, then it has unique identity proofs. And so I thought that, yeah, this was nice, but with like modern proof assistance, like ACTA or ROC, I could formalize this more directly. And since I had learned that people in this area communicated a lot via blog posts, I thought, well, okay, let's do that. So I wrote a blog post, and then something amazing happened, namely Martin wrote to me about my blog post. And yeah, that was extremely encouraging for me. And then what followed was that, well, Martin shared his research questions with me, and we had long discussions and several visits. And we wrote 2 papers together. And well, okay, I know that 2 is maybe a rather small number, and many people here probably have much more impressive numbers. But for me, these 2 papers were very, very beneficial because it taught me what I could do in this area. Right, and of course, reference letters, of course, one bad thing in academia is that if you want jobs, or most people, including myself, have to write many applications, and then someone has to write reference letters for these many applications. So yeah, thanks again for that. Okay, so for this occasion, I thought I'd just go back 10 or 12 or 14 years and see what we had done at that time. So most of what I'm going to say, or maybe all of what I'm going to say, is already like more than 10 years old. But yeah, at least it was interesting for me to revisit it. So in 2012, one of the questions that Martin asked was, well, say you have some function f from a to b, and you know that it's constant in the sense that it maps any two inputs to equal outputs. Does this function factor through the propositional truncation? So now if you're in some set-based, well, propositional truncation essentially means that the function only knows that there exists something in A, but it cannot actually check what exactly A is. So if you're in some set-based world, either in H sets or in type theory with some assumption of UIP on B, or in set theory, then this is a very reasonable expectation. It does not quite work with general types, but there is one interesting special case where it actually works, namely if f is an endo function from A to A. And so I remember thinking about this problem with Martin, and Martin also remembers this. So just last year, he told this story on social media that, well, a long time ago, that was actually 2012, he gave me this question, and Martin says that I solved it in the evening and then said I also formalized it in Acta so that when I wake up in the morning, it will still be true. I think the story is mostly correct. Just the only thing which I would like to correct is that I probably solved it, well, no, I certainly solved it during the night, and I would never have claimed that it would still be morning by the time I would wake up. But so, well, this problem, I mean, was difficult for me at that time because like solving it required me to figure out how up and transport and path composition and all these things interact. So this is now completely standard. And what I produced at this time would now be considered a very ugly path algebra proof. So some years later, when Christian Sattler looked at what I was doing, he came up with a much nicer argument, which happens very often when Christian looks at what I'm doing. So the much nicer argument goes like this. So you want to show that this type of fixed points is a proposition. And you can do this by showing that if it's inhabited, then it's contractible. So you assume that you are given some element of this. Let's say you actually only need this A0 in A. And then in this fixed point, in this definition of the type of fixed point, you replace f of A by f of A0. And so then this type suddenly becomes a pair of some element A together with an equality which specifies what A is. And this is the typical shape of a contractible type. Okay, right, so here's the other case in which Martin's question had a positive answer, namely if B is a set in the sense of homotopy type theory, so it's an H set. So in this case, functions from the truncation of A into B are the same thing as these constant functions from A to B. So this is a quite simple fact, and it's nowadays contained in all hot libraries because it's actually quite useful. So here I'm just giving some, well, at that time Martin wrote a proof of this in an email. I'm now giving a slightly different argument and probably an unnecessarily complicated argument, but it will be useful for what comes later. So the first observation is, well, let's actually get rid of this assumption truncation of A. So let's just say we are given some A, then this canonical map from B to the type of constant functions from A to B is an equivalence. And well, if B is a set, then this is very easy. Like if you have any such function and you want to know where it comes from, you can just apply this function on this point A that we assumed, and it gives you some B. And then since well, then you can use this constancy argument to see that this is actually the only B which could possibly be in the pre-image. So the pre-image is contractible. And now the second lemma which can be used here is, well, it's standard that if you have an equivalence, then composing with this equivalence is again an equivalence. But you can actually strengthen this a bit and say that, well, if X implies that some map E is an equivalence, then the composition with this map E with some map from X to Y is also an equivalence. And now you can use this. I mean, you can apply the second lemma on the first statement here to get this this truncation A here back. And on the right side, it actually disappears because it gets eaten up by this assumption A, which is here, and this assumption A, which is also in here. But on the left side, it stays, and then it gives us what we want. Okay. Right. So then after doing this, well, I had found something which kept me awake at night. So I started thinking about, well, how can I formalize this? Well, how can I generalize this statement? Because I don't want to assume that B is a set. So now if B is a one type, well, then it still works, but I need to add one more condition on this constancy proof. So I need to add the coherence condition, which says that, well, essentially, if we compose two witnesses of constancy, we get the witness of constancy that we would have expected. And so the proof is very similar to what we did. The difficult thing is showing that if we assume that we have some point A0, then this canonical map, which goes from B to this function of, well, coherent constant functions, is an equivalence. And well, here are some slides that I made when I was a PhD student and when I had much more time. So the trick is, well, let's start with B. I mean, let's start with B, like this B here. And then we just transform this, and in every step, we don't actually do anything up to equivalence. So in the first step, we just, well, we really didn't do anything. We just added a unit. And then in the next step, well, we add to this data which we had, we add a function A from A to B. But in the same step, we immediately say what this function f is. Namely, this function is exactly what we already had. And this is a contractible pair. So this step, again, doesn't do anything. And we just do this again and again and again and again. And then, well, once we have done this a couple of times, I actually start deleting contractible components. And I'm not going through this in detail because it would take a bit long. But if you do this for long enough, then well, what remains is exactly what you wanted. So what remains is exactly a function f, a proof of constancy, and a proof of coherence. So from B, we didn't actually do anything. We just added and deleted some contractible components, and suddenly these coherently constant functions are left over. Right. So now the nice thing about this argument is that, well, it really doesn't require anything. So it works. I mean, this fits very well with Martin's Spartan type theory approach, because this really works as soon as you have unit, sigma, pi, identity, and truncation. Actually, I don't even think you need truncation, to be honest. Yeah, I don't actually think you need truncation to do this. I mean, you need it if the statement you want to prove has a truncation in the end, of course. But like in order to do this expanding and contracting strategy, you don't need truncation. No, it doesn't. Oh, the other side. Okay. Yeah. So right. Okay, but now here's the issue. Like, if we want to do this in full generality, so we don't just assume that B is a one type, but we don't assume anything on B, well, it still would work, but we would have to do this infinitely many times, and we can only do this if we have some notion of infinite sigma types, which Mike Schulman introduced as really omega op limits. And they are similar to, I think, Hickman's very dependent types. So if you have some feature like this, then you can do this in your type theory. Two people have independently, to me, pointed out that this can be seen as a generalization of some proposition in Lurie's higher topos theory. So one person was Wołodzki and the other person was an anonymous reviewer, but I think they might actually have been the same person. Right, so now if we actually just want a result that we can state and formalize in hot, we would say that, well, let's fix some number n, and now if B is an n-type, then the functions from A truncation to B are the same thing as constant functions from A to B with n levels of coherence. Right, so we can formalize this in hot if we fix this number n. So now this is the issue. So a coherently constant function is, well, essentially a map between semi-simplicial diagrams, namely from the co-skeleton of the constant A diagram to constant B. Just when I say constant, I mean, we have to take a really vibrant replacement first, otherwise this doesn't make sense in type theory. Yes, please.
We have to state the Liori result. No is an acceptable answer. Like if you can remember it.
Sorry, say again, please.
The Liori result in the previous slide. Can you say what that is?
Well, it's not possible to state this without like introducing quite a bit of terminology.
If you already know,
but I would have to check the terminology myself. So, yeah. Okay. Right. So this is easy to write down if we know how high we can go, but encoding it in type theory for some, well, variable n is an unsolved problem. So I can only do this if you tell me in advance which number n you want. So it's like a family of proofs in homotopy type theory, like one theorem for every number n. And so how could we formulate this in hot without this issue? So one way to do this would be to use Wołodzki's homotopy type system, where you have a type of strict natural numbers available, which then even is identified with the internal type of natural numbers. So this would work, but it's, well, at that time, I thought it was not satisfying for me because I really want some results in homotopy type theory. And this is not homotopy type theory, it's some new type theory, right? But so what convinced me that something like this works is Paolo Capriotti's conservativity argument, which says that two-level type theory, which is essentially Wołodzki's HTS without assumptions, is conservative over hot. So in two-level type theory, you can actually formulate this theorem, which we had, and then you can, well, instantiate it with a particular number n and actually extract some homotopy type theory theorem. Okay, yeah, so thanks. That's all I wanted to say.
You turn your mic off. Do you have any questions?
I did have a lot of questions back then.
Do you have any, like, if you don't want to fix the level n and you want to have, like, if you just want to have a general theorem, do you know of an answer?
I mean, of course, there are encodings of the propositional truncation, like alternative constructions of the propositional truncation in the sense of what expert bracket did or what Floris did or what I also did. So this would also characterize what such maps are, because you could unfold this alternative definition of the truncation. But that's, of course, not really the same thing. So if you do that, then this would add an enormous amount of additional redundant data to this very nice characterization of saying that query constant functions are just these maps between single integral diagrams. But yeah, I mean, it's like the same problem as always. Like if you know what we want to express, but in order to express it, maybe we have to add lots of redundant data to make it uniform enough so that it's expressible in the language.
I think we should advertise this as our community has some open problems about constant maps.
Really?
I wonder, Theorem, does he have a computational semantics? Does he have the canonics?
Yes, it's. I mean, it's. Well, two-level type theory is actually an extremely simple device. It's just like when you, like, say you want to prove something in some category C. Instead, you just prove it in pre-sheaves over C. And then if you restrict yourself to the representable ones, it's the same as the original category, but you just have more additional language. And this additional language is exactly what two-level type theory adds to homotopy type theory. Mm-hmm. But in terms of computation, it's really the same. I mean, but in terms of computation, it's really, you can really think of it as intentional Martin-Löf type theory, maybe with UIP, maybe with UIP, like some form of extensional Martin-Löf type theory. You can use ACTA if you want.
But it doesn't normalize this.
But
Yes.
you don't even need extensional type theory.
Sorry, say again?
You don't even need extensional type theory.
It works.
Yeah, you can use intentional type theory. Yes.
But
Yes.
does it normalize it?
Yes.
It's trivially, I mean. But
Yes.
sorry, but you can also add that the natural numbers, I mean, what's co-fibrant or something, and then you get the semi-simplified types internally, right?
Yes, you can do this, but I mean, then you're back at this problem. I mean, yeah, it's of course a valuable thing that you can do, but I mean, then you're back at this problem that what you're doing is not homotopy type theory anymore. So to me, it was important that the theorems that I prove can be formulated in homotopy type theory, or at least some special cases can be formulated in homotopy type theory. Because if you start proving theorems in some new type theory, which maybe one or two other people have thought about before, and like how do you connect your stuff to what already exists?
I mean, okay, you add an extra principle, an extra axiom. Why is this so terrible? I mean,
I don't know.
I mean, okay, I don't even know. Does this reduce? I mean, if you have this, then we can.
Sorry.
Yeah. Just maybe it's just the same question that Andre asked in a different way. But so is it then therefore not known if the sort of internal statement inside hot for all n, it's not known if that is true, right? It's like semi-conditional types. You don't know if you can build them, kind of thing.
But the problem is that you don't even know whether you can make this statement.
Yeah.
Internally.
Yeah. Okay.
So formulating the statement is probably as hard as proving the statement.
See. I mean, could it potentially be? Well, I guess maybe it's not true internally. Maybe Hart doesn't believe it.
Yes.
It may be that you cannot formulate it.
Yeah. It's independent of.
No, independent because you cannot say
Cannot formulate it.
it.
No, but here we have a consequence. So hang on. What you do here is something you can say. Oh, not what we can.
So, I mean, I think if you can formulate it, then you can prove it.
You have the proof term, you just don't have its type.
Like a physicist say, it's not even wrong.
I will be constant. That's not.
Okay, I think we should end it there before we dive into Martin. Okay, the last word.
It's actually not quite a question to you, but last weekend in Ljubljana Discord, Andre started asking questions to me about constant maps. And he said he wouldn't because he was going to say something this week. But
But you wanted
you
to know
did-
why I'm asking this, and I
Yeah.
said I can't say.
But so now can you say?
Oh yes, I was trying to fiddle with the construction of the schiffification, and it came up that I was trying to push this equalities here and there, and one of the possibilities was that I need something to be constant, and
I see.
but it didn't work out.
If somebody waiting in the online, they have a question. Sure, so answer.
We need to move on now to the next speaker. Okay, so let's thank Nicolai again.
Probably Gary already knew what I was talking about, and I think this time probably